I'm gonna try to record this. Great. It says I'm recording, so okay. Like I said, it was the old noggin had to work extra hard for some reason. I don't know. Okay. Good. I'm not on mute. That's an issue sometimes if I'm on mute. Okay. I think we're doing it, guys. So hopefully I'll be able to record this one as well. And then obviously next one and the following one if this one works. But this is kind of my test run, I guess. So hopefully it works. I don't know. But you've survived this far, so we'll see. How was the test? They should be available. That was my bad because I had only checked, or like I didn't check to make sure that they were all checked off. It was just available at 4:30, but
now they should be available.
Yeah, should be up now. So nice work. Just like for quiz 1, right? If you just come see me, we can have a look at both your tests and just have it go through which ones you got wrong. Intimidating because this is why it's wrong. No, no, I think it's really good to just kind of walk through the ones that you got wrong and just kind of see what happened, especially for the final exam, yeah, which will be the same layout, exact same situation, right, just longer. So, because we'll have 3 hours. 3 hours of this, whoa, I know, right? So like I said, for that chi-squared calculation one, I'll have to go back in and manually check that how you did on it, and then I'll boost your grade by 1 mark if you got it, right? So bonus marks work, I guess. All right, any questions before we start ANOVAs? Then I have a question for you. Were you disappointed when you read about ANOVAs? What? Yeah, so what's new here? Well, nothing really. Now that you know the name of the game, right? And so analysis of variance has very little to do with variance, but it analyzes the variance in the background, so that's why it's called that. But an ANOVA, right, is really if you just have more than 2 groups and you want to compare their means, right? So we've looked at the 2 independent samples t-test, right, where we've got 2 groups, 2 independent groups, and we want to compare their means, right? And so now if we just have more than 2 groups, then what we do is we use an ANOVA, right? And so let's see if I can get my writing up to, well, snuff, let's say. So recall a 2 independent samples t-test Can you guys see that? Is that okay? Good. Okay. So recall a 2 independent samples t-test. It's so boring because I'm down here. Hello. Essentially has a null hypothesis, and bear with me, I'm going to get a little crazy here. Right? The null hypothesis is that the mean of group 1 is equal to the mean of group 2, right? Or not significantly different. So how we could write that is that mu1 equals mu2. Right? The mean of group 1 is not significantly different from the mean of group 2. Right? So now, if I give you the null hypothesis for an ANOVA, right? These should be means, but because of the font, but I can, or mu1, or the null hypothesis, I'll clean that up, sorry guys. mu1 equals mu2, which equals mu3. And it just leaves room for as many means as you need, up to k means, however many k is, right? So this is how many groups you have, right? 1, 2, 3, up to k groups. You're still measuring at the interval or ratio level, right? You have to have numerical data, okay, split amongst these groups. Okay? And then your alternative is that at least 2 of these means are not equal, right? So the ANOVA will not tell you which ones are different from each other, right? It'll just give you an overview and say, hey, there's one in here that's different from all the others, right? And so ANOVA will not detect specific differences only tell us if there is a difference. Easy enough when we just had 2 groups that we were comparing, right? Well, if they're not the same, then they're different, right? Here, the null hypothesis has to be that, yep, they're all the same. Everyone's the same until we've proven otherwise, right? That otherwise has to be that, well, one of these is significantly different from at least one of the others, right? And so we don't know how many or anything like that. And so what we do is, if we have a significant ANOVA, then we know that we can go in and we can test further, right? Then we can do pairwise comparisons, right? Maybe we have some idea of which ones are significant, right? But it just gives us an overview, just like the chi-squared did, right? So the chi-squared also just says, hey, there's an association here. I can't tell you what it is, but there is, so you need to look at that, right? Same thing with the ANOVA. Any questions about that? Right. So you guys are at that point now, that kind of fun point where you're hopefully getting a little bit more comfortable with hypothesis testing, right? So we don't need to talk about hypothesis testing so much. Now I can just introduce a test, ANOVA. I can give you the null hypothesis, and then the p-values and things like that, they behave the same, right? As they always have. So if we run an ANOVA, and you guys would never do it by hand, so we're gonna use Excel to do it, right? And so what we're gonna get though is an F statistic. We've already seen an F in the Levine's test, right? So we've already seen Fs. We don't really care how they behave or anything like that, but it's gonna calculate an F, and that F is gonna give us a p-value, right? And so at the end of the day, we're just gonna get a p-value. And if we know our null and alternative hypotheses, and we have a p-value, then the stuff in the middle isn't that important for us, right? Because at this point, right, if you get a p-value that's small enough, then you can reject the null hypothesis and conclude that there is at least one mean that's different from the rest, right, in the ANOVA case. So we can talk about what the F statistic does, but essentially, so it, like I said, it analyzes the variances between the groups, within the groups, and it just tells you how big the difference is. But again, it doesn't tell you which the differences are, so it's not, we don't need to know that much about it. Okay? Because even though, okay, so we've got this little note here. So when the F statistic is close to 1, it indicates that the difference between the groups is very similar. And so we would probably not be able to reject the null hypothesis. But you're just gonna look straight to your p-value, right? Only make decisions based off of your p-value, right? And so only make decisions based on your p-value. Oh, I guess I should. Any questions? No? Kind of same, different slide. So again, if you've got a significant F, right, or an F test, then, right, you've got a small enough p-value. And so if F is large enough, the p-value will be less than the alpha level, right, which we're just going to go ahead and assume it's 0.05. This doesn't look like a word. And the alpha level, yeah, which means we can reject H naught, right? But still just based off of the p-value, but I just want to make the connection. Bless you. We can reject H naught in favor of HA. I'll start with therefore. We can conclude at least one of the means is significantly different from the others. Therefore, we can conclude at least, oh, turn my at into a line, come on. I have to turn that feature off, I think. It turns all my letters into just lines and triangles if I'm too sloppy. Therefore, we can conclude at least one of the means is significantly different from the others. All right. So we have to talk about the appropriate use of ANOVA or assumptions. These should feel pretty old hat by now, right? There are a lot of the same assumptions that we have for the t-test. In fact, it's a little bit less than the t-test, right? And so we have to have independent samples. And so each of our groups have to be independent. So samples need to be independent. So what that means, if I just pull it down here, is that groups must be independent. Right? and ideally random. Here's where we get into kind of the wishy-washy stuff. Well, if we can have exactly what we want, yeah, we would have random samples. That's not always going to be the case, right? And so ideally random, we're kind of loosening that restriction. Again, like we said, we have to have measurements at the interval or the ratio level. If we don't, right, then we would have a chi-squared, right? Nominal or ordinal. And so the interval or the ratio level means that we have numerical data, right? Meaning that we can take measurements, and that's the only way for it to make sense that we're talking about a mean, right? And so for numerical data, so we need to have numerical data in order to calculate a mean, right? We can't take an average of genders, for example, right? It just doesn't work, right? As soon as you can talk about the average of something, height, weight, distance, speed, right? All those are measurements. You've got numerical data, and then you can take it, you know, to the interval or ratio. But I like just the numerical categorical distinction, right? And so we need to have numerical data in order to calculate a mean, right? And a mean is an average. Oops. A mean. Oh, hey, that turned into a nice O, but now it looks weird. Or average. That's all stuff that you know already, but just want to talk about it again. Okay. It's also good, but not absolutely essential, for the sample to be normally distributed and have homogeneity of variances. Homogeneity of variances, right, is just, can we assume equal variances, right? But now, because we've got more than two groups, right, we're just going to expand it to homogeneities. Still saying, are they equal across, right, or relatively equal? But the F-test can actually withstand quite a bit of unequal variances, so it's not something that we care too much about, right? The t-test is a little bit more finicky, and so that's why we had to use the Levine's test, right, to check, do we have equal variances or not? And then, so the F-test is a little bit hardier, a little bit more robust, and so it can handle some unequal variances and not be too fazed by it. Okay. Any questions? Okay, so there's ANOVAs and then there's repeated measures and ANOVAs. Repeated measures ANOVAs are a little bit more powerful just because you're repeating measurements on the same subjects, right? And so you've got this kind of flow and timeline information that you know, right? And so if you're able to do a trial, right, where you've got repeated measures on the same subjects, now you've got repeated measurements on the same subject, right? And so those are going to be dependent now, right? And so it's a little bit different. But it is more powerful, right? Because then we can follow through and say, okay, overall, you know, these people saw this change, right? And so it's a little bit different, but just remember that we're repeating measurements on the same subjects over time, right? More than twice. Otherwise, if it's just twice a pre and a post score, then you can use a dependent samples t-test, right? So now it's more than twice. But This is similar to, I guess I'll put it on here. This is similar to a dependent samples t-test. Since observations in each group will be dependent. But we've made measurements at more than 2 points. We have made measurements at more than 2 points. Right, because 2 points would be a t-test. All right. Sometimes when I go through these, you know, when you go to the pharmacy and, I don't know, let's say you're getting birth control pills, I don't know, but they always have to tell you about the risks and everything. I'm like, yeah, here are some things that we need to be aware of. But anyways, here's some things we keep an eye out for. If you've got a trial going on, right, and subjects are being exposed to more than one treatment, you need to take that into consideration, right? And so there's things that you can do, right? The order of the treatment might have an impact. So maybe what you want to do is you want to randomly assign people to different groups, right? I think the textbook she uses, is it chemo and surgery, I think, right? And so you want to randomly assign people to different groups, right? So not everyone goes to chemo and then everyone goes and gets surgery. And then we're trying to conclude that the surgery made a huge difference, right? That's going to be very hard to do. And so same idea, right? You could have carryover effects, especially in health, right? If people have been on some drug, right, for a really long time, then maybe we need to let that kind of settle down, get levels back to normal, before we go ahead and use these treatments that we're trying to use to prove a theory. Okay. So ANOVA Results, which is in reality just all that you'll be reading, right? If you're reading reports or journals and things like that, right? They're going to report some F statistic. Okay? And then there's going to be two sets of degrees of freedom. There's a numerator degrees of freedom and a denominator degrees of freedom. You don't need to keep track of those, but here, this is the numerator degrees of freedom, and this is the denominator degrees of freedom. And in case you care, if you have a fraction, the numerator is always on top because he's numero uno. The numerator over the denominator. Right, it's a fraction. Because the F statistic is a fraction, right? And so we've got degrees of freedom for the numerator, degrees of freedom for the denominator, and together, right, they help us pick a value in an F table. And I didn't even bring one because you don't need it, right? Just like the chi-squared table, the T table, there's Z tables, there's tables for everything. right? Because there was a time when software was non-existent, let's start there, right? Or really expensive. Now our phones can do an F statistic and we don't really think much of it, right? And so there was tables for everything, but now we don't really need them, right? Because whatever software we use is gonna just give us a p-value, right? And so I gave you the chi-squared table, right? Because doing a chi-squared in Excel is kind of hard, or it's just unruly. But for things like this, t-tests and ANOVAs, we're just going to use Excel to do it, or SPSS or R, if you're so lucky. But there's lots of softwares out there, and they'll just give you the p-value, right? So K is the number of groups, right? And so remember, we're comparing the mean of group 1 to group 2 to group 3, 4, 5, up to K groups, right? And so K just denotes the number of groups. N is the number of participants. So how many people did you collect information on, regardless of the group that they're in? And then, so if you've got the numerator degrees of freedom is K minus 1, right, and you've got 4 groups, then you have 3 degrees of freedom in your numerator. And let's say you collected, 50 people, right? Then, and you've got 4 groups, 50 minus 4, 46 usually, hopefully, is your denominator degrees of freedom, right? But like we'll see, Excel just does that for us, right? We just need to know, oh, there was something, this is you guys in about a year. She mentioned something about like degrees of freedom, and there's 2, I don't know. Just look it up. Yeah, that's good enough. I'm happy with that. If you can Google stuff, that's good. Right? And so F has to have 2 degrees of freedom. And then there's an overall degrees of freedom, but it doesn't actually factor into the table or anything. So I just kind of scooted it down because we don't really care about it. So if you're reading an article, right, up here we use the degrees of freedom in the subscript, but that can get kind of hard to read sometimes, especially if you have to have really small print. And so usually what we do is just do an F, and then in brackets, same idea though, right, is we have the numerator degrees of freedom and the denominator degrees of freedom, and then what that F value equals. But then they'll also report the p-value, right? So based off of this p-value, who cares what this is, right? This says that I can reject the null hypothesis, right? Because it's 0.01, and so that's less than 0.05, right? And so now I can say at least one of these means is not like the other, right? So if we've got 2 degrees of freedom in the numerator, how many groups do we have? Must have 3, right? So we can work backwards that way too. We wouldn't have to, right? But it's all part of the fluency, I guess. And then if we've got 120 degrees of freedom in the denominator, that's the same as n minus k. And we just decided that we must have 3 groups. So our n must be 123, yeah? So you can kind of work your way, snake your way through. Okay. But the most important thing is you get a p-value and you know what to do with a p-value. Okay. Questions? I figured out how to put emojis in here. And I almost got carried away, but then I was like, no, 1 cool guy is enough. So it's like I deliver the whole lecture. All the slides are purely emojis and numbers, 100. Maybe I could, maybe I couldn't. Did I hear challenge accepted? Yeah, you got it, you got it. Twice as many slides. It's like, here's what I meant to say. Got it? Because I have to have a test run, right? Where it's like, okay, here's what I meant to say. Did I communicate that? Oh, okay. Oh, this should be pretty fun. Okay, so remember, right, ANOVA only tells us if there's a difference somewhere, right? If there is a difference, then we have to dive deeper, and typically we just go and do t-tests all around, right? We're kind of bummed that we have to do that, especially if there's like 10 groups, right? This one with this one, 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 this one, blah, blah, crazy, right? Another thing to keep in mind is that each of those t-tests that we do have the same type 1 error. And so for each t-test that we run, right, we're just adding 0.05, 0.05, 0.05, 0.05 to our type 1 error until eventually it's just going to be huge, right? And so that's not good. There's methods in place. You can do a Bonferroni correction, which beyond the scope of this course, right? So there's methods to deal with that where we just take, you know, we split up our alpha level into something smaller, for example, right? The easiest correction would be, okay, instead of rejecting at 0.05, if I have to do, to make it easy for me, if I have to do 5 t-tests, then I'm going to decrease my alpha level to 0.01 for each of these, right? Making it harder to reject each time. But at least then if I'm rejecting, then I know it's for real, right? That's like the simplest option. Whenever you're doing these, I almost said post hoc, kind of follow-up analyses, right? These are called post hoc analyses. And so if you run an ANOVA, then whatever you do after is a post hoc analysis, right? And so, and people love to throw that word around, but don't be scared. You have done post hoc analyses, right? You just don't feel like it, okay? And so, yeah, employers especially. Oh, well, can you do, like, how's your comfort level with post hoc analyses? Do you know what it is? It's just t-tests after an ANOVA, for example, right? And so it's nothing scary. And then, yeah, there's other things that we can do. But as the cool guy emoji says, we don't care. We don't need to care. All right. Any questions? So I think we've got an example up next. All right. And this is where I get a little bit worried with my setup, but we'll see how it goes. Okay. And if you looked at the slides I posted yesterday, I added the ANOVA example today because why didn't I have an example to begin with? I have no idea. I don't know what I was thinking. Anyways, so I stole this from a textbook, as you do. And so a random sample of 40 women is partitioned into 3 categories with ages below 20, 20 through 40, and then above 40, right? Now we've got these 3 categories. Even though this is numerical data, right, the ages, we can talk about the average age, but whenever we have numerical data, we can convert it into categories, right? We can't take categories and convert them into numbers, right? That's not going to work. But we can take numerical data and we can make groupings to make categorical variables. So the systolic blood pressure levels are obtained from the fhealth.xlsx spreadsheet posted on Moodle. And I stole it from Triola and Triola. is there evidence to support the claim that women in different age categories have different mean blood pressure levels? Yeah. We can set up our null and alternative hypothesis now, right? And then we'll go and use Excel to do the actual analyses, right? And I posted the data set on Moodle if you would like to follow along, but just stick along for the ride. All right. Oh, I need more. How about add a page? I'm all proud of myself, but it's not like I haven't used Notability for years already. Like, yeah, I know how to add a page. I don't know. Okay. The null and alternative hypothesis. All right. First thing I'm going to do is, just to simplify things, is I'm going to just label these groups not less than 20, between 20 and 40, and then over 40. I'm just going to let them be group 1, group 2, group 3. But in order to do that, I do have to say what I'm letting group 1 be, group 2, group B, and group 3 be. And so I have to say let group 1 be the below 20 group, bless you. Group 2 be the 20 to 40 group. We can't have overlap, right? Remember, basically our one condition was, for just a basic ANOVA, was that these groups have to be independent, right? And so the below 20 is not including 20, right? The 20 to 40 includes 20 to 40, right? And then the over 40 starts at 41 and over, right? So, and then group 3 is the over 40. H naught. Because it gets a little, well, way too wordy for me, and I think you can handle it now, I'm just going to use the mu notation, right? The mean of group 1 is equal to the mean of group 2, which is equal to the mean of group 3, right? You could write that in words, right? The mean of group 1 is the same as the mean of group 2, which is the same as the mean of group 3, right? And the alternative hypothesis, we don't want to say that mu1 doesn't equal mu2 and it doesn't equal mu3, right? Because we don't want to specify which ones are not equal, and it won't tell us which ones are not equal, right? And so we're just going to put the blanket statement out there that at least one of the means is different from the others. Null hypothesis, alternative hypothesis, done and dusted. Here we go. Are you guys ready for this? I guess am I ready for this? Okay. So now we're going to use Excel to find the p-value. One thing to keep in mind is that to use Excel for ANOVAs, or to run ANOVAs in Excel, the data has to be in a specific way. Okay, so to use or to run an ANOVA in Excel, the data must be set up, oops, set up like this. We need group 1, group 2, and group 3, each in their own column. Okay. And then we've got X1, X2. These are just the observations, right? X3, X4, da 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 da. Group 2, I'll denote by, I don't know, Y's. Group 3, Z's. Pretty common practice. I'm not making it up, guys. No. I didn't come up with these myself. Y1, Y2, Y3, Y4, etc. Oh, and then I said Z for group 3. Z1, Z2, oops, Z3, Z4, da da da. Okay. One cool thing is that the sample sizes in each group don't have to be the same. Okay. And so the sample sizes in each group do not need to be the same. Should insert the cool dude emoji there. Cool. All right. So here's where my switcheroo happens. Does anyone need this before I switch? Your internet connection is unstable. That is not ideal, actually. Oh well, there's nothing I can do about that. All right, here we go. Stop sharing. Okay. And now I want to share this. Okay. All right, all right, all right. I know that's really tiny. Maybe we don't need, we can just look at the top rows for a bit. Yeah. All right. So here's kind of a typical data set, not those nice, clean things that you've handled up until now, right? But we can handle this, okay? One thing that you'll probably notice the more if you look at spreadsheets a lot more, most programs can only handle single words. So we usually make use of underscores, kind of camel type, which is where you capitalize the first letter of each word and then you just put them together. Anyways, or you just use single word or abbreviations or whatever. So a lot of these, we could probably figure out what they are, right? And so here we've collected data on 40 females. Is there an mhealth.xls? Yeah, you bet there is, right? With males of the same stuff, right? Could we compare the means of the males and the females? Yes, absolutely, right? But that's for t-tests. We're not doing that. But we could. Each female has an ID number. We don't want to take the average of this, right? Because this is essentially a categorical data. right? Each ID number is its own category, right? So it's not important, but any data set that you get will have ID numbers in there. There's the age, that's pretty obvious. Hey, there's a 12-year-old in here? I thought they were all nurses. Okay, well, that's even the 16, 17, 18. I'm weirded out by all those. But anyways, maybe they're not nurses? Logical explanation is that they're not. But anyways, we've got the height. Not in centimeters, I'll tell you that much. The weight, yeah, probably pounds. The waist, I'm assuming, is just a measurement of the waistline, right? We can assume. The pulse, the systolic pressure, you guys, diastolic. Help me out here. Col must be cholesterol, BMI, leg, elbow, wrist, arm. Probably measurements of the leg. I don't know. It doesn't even make sense. What do you guys think it is? Yeah, how do you measure the elbow? It's like how many rotations? Maybe it's the circumference of the elbow? Everyone's feeling self-conscious. Wrists, arm. Like, now that we've gone over those very important body parts, we can do some stats. Okay, so we've got information on all of these. A lot of the time, right, we can just figure out what these are. There's usually a data dictionary where it actually defines what they are, but here it's pretty obvious. So we want to do an ANOVA, right, to compare the mean systolic pressure in each of these groups. But they're not in groups yet, dun dun, right? So we have to make the groups, but we can do that with a little bit of problem solving, right? What would you do? Age. Oh, look at me. It looks like I was nice and I sorted them already. But even if they weren't, right, then you could just sort by age, right? Make sure that you're sorting across all the rows, right? And so let's pretend that these weren't sorted. Actually, you know what I'm going to do? Just to show you guys. Where am I? Sort. And your Excel might look a little bit different, but there's always a sort and filter option. And so I want to sort the ID numbers from smallest to largest, only to jumble up the ages, right? And so what I'm going to do is it'll ask you, data outside your current selection won't be sorted. What do you want to do? I want to expand the selection. Obviously, I don't just want to sort this one, because then all those IDs are not attached to the measurements anymore. Sort. Okay. Mission accomplished. Now my ages are all jumbled. Imagine this is what you got. Okay. First thing, we're gonna make categories without actually making categories, right? So we're gonna sort the age variable. So same thing, I'm just gonna undo what I did, right? But highlight the age column, and then I wanna sort from smallest to largest probably. I wanna expand it. Voila. Okay. So now, what I want is in my first column. Remember, Excel wants group 1 data, group 2 data, group 3 data. Right? So what I'm going to do is I'm going to just pull out all the systolic measurements for everyone that's under 20, right? And so 12, 16, 17, 18, 19, 19. I'm going to highlight all of those measurements. Okay? And I'm just going to copy, little copy pasta. And then in a new spreadsheet, right, you can open up a new sheet down here. Oh, it's so tiny. All right, and we don't need it to be so tiny. Up here, I'm gonna just say group 1. You could say under 20 if you want, and then I'm just gonna paste it in. Right. I'll make labels for group 2 and group 3. Oops. And then I'm just gonna go back and I'm gonna retrieve everyone between the ages of 20 and 40, their systolic pressures. I don't actually care about their ages anymore, right? I'm just using it to pull out the systolic pressures that I want. So I go back and start here, 22, including 40, we said? Cool. Copy, paste. Luckily, we don't have to have the same number in each column, right? So that's good. So this is fine. It'll take that into account, right? But we don't need to worry about it. And then everyone else goes in group 3. Okay. So I don't know how comfortable you guys are with Excel, but you want to make sure that you have all 40 entries from before. So what you can do is you can just highlight all of these guys, and then down here it gives you a count of 40, right? So it tells you that you got all 40. So that's a good kind of checking point. It gives you a sum and stuff and the average, which won't make sense a lot of the time, right? But you could look at just the one column and it would just give you a quick overview of the average systolic pressure for group 2. Right now it makes sense. And the count in group 3 is 23, right? So it just gives you some quick information. Okay. So far we're doing it. We're really doing it. So now we're ready to run our ANOVA, right? We've set up the data the way that it wants it to be. And so now if you go to the data tab here, you should have the data analysis tool pack installed, unless maybe you did an update or something, but then you'll have to go grab it. Okay. All right. So if you go to the top, it gives us 3 options for an ANOVA. For us, we're only doing a single factor, okay? Meaning there's only one grouping variable, the age, right? For 2-factor, we can have essentially a chi-squared, but it dices it up with the numerical data, right? So we can have age and, I don't know, some other category, gender, male, female, if we combined all our data sets, right? Something like that. We're not going to deal with that, obviously. So we're just doing a single factor. And so if you hit that and then hit OK, the input range, it just wants you to highlight all of this, right? And you know what? Just for nice output, I'm also going to highlight the labels, but then I'm going to tell it that there's labels in the first row. Okay. So if I dive in, including the labels, if your spreadsheet looks like mine, you should be going from A1 to C24 in here, right? Your input range, if you've included your labels. It asks if it's grouped by the columns or by the rows, right? We could have done it by the rows. I think that's just weird. So we're just gonna do it by the columns. And I'm gonna tell it that there's labels in the first row. We're gonna keep the alpha at 0.05, that's fine. And then I'm just gonna have the output range in the same sheet, maybe E1 for Emily. And now we're ready. Are you ready? I know you are. Okay. So it gives us this output. That's a lot more output than we're used to, right? But if you just kind of break it down, these are just summary statistics, right? And so you've got group 1, group 2, and group 3 each have a count, right? We counted group 2 and it had 23 and we're finding 23 still. Is that a question hand or just a hanging out hand?
I'm just dealing with it.
Yes. Ready to smack it? Yeah. That's all right. It's got the sums and the averages and the variance of each of the groups. We don't really care about that, right? Maybe the averages, right? But we use the ANOVA because we've got more than 2 to compare them. So here is the output for an ANOVA, and this is what you would have to do by hand, and it's doable, but why would you want to when it's so easy in Excel, right? And so it's got some variation, blah, blah, blah. We don't really care about anything up until your F statistic, right? So the F statistic is the same as the chi-squared, right? And the t that we calculated calculated z's, right? So this is the value that tells you how far apart things are. It also gives you the p-value, right? It's also giving you the critical value for F, meaning, okay, so remember how we use the table for chi-squareds? Anything past 3.84, we would reject the H naught, right? The 3.84 was the critical value. And so here what it's saying is you would need at an alpha of 0.05, because remember we told it that? We would need an F of 3.25 in order to reject H naught. That matches our p-value of 0.205, right? 0.205 is not less than 0.05, so we don't have enough evidence to reject H naught. Right? And so this is not bigger than this, and this is bigger than 0.05. They're all linked. Okay. Let's see. Okay. Things are gonna get weird. So I'm going to try to screenshot this. Okay. So now we've got all our information from Excel, so I'm going to stop here, and then I'm going to, oops, start here. I'm really just talking myself through it, I guess. Here, hang on. Good. Okay. I did a mask with my sister this weekend. But more importantly, it's like got hot in here, huh? But also, here, I'll show you guys. Just to detract from, oh, here we go. I'll have to put it here. My mom has a ton of puppies right now. And they're all gonna be little guide dogs. Oh, I should have said cute awes. Oh well. Okay, but this is actually not the photo I was grabbing. Okay, so got a little distracted. It's my sushi. Oh yeah. Not a lot going on there. Okay. Do I have to delete this puppy picture? Probably. Okay. Feeling pretty proud of myself for this one, actually. All right. Try to make it bigger. Whew. All right, we're doing it. Whoa, back here. Identify the name and the value of the test statistic. The name, it's not as hard. It's just an F statistic, right? And what's the value of it? It was 1.65-ish. So the ANOVA calculated the F statistic, or the value of the F statistic. Hey, that said value. All right. The value of the F statistic to be, and I'm going to throw in approximately just because of math hang-ups. Approximately 1.65. So the name of the statistic, it's just an F statistic. It's not important. All right. Identify the p-value. Hey, we're ripping through these things, because we did all the work already. The p-value, oops. The p-value is 0.2. Should have, oh, come on. Gives me a chance to say approximately, so I don't have to write it all out. Approximately 0.205. Right. What does that mean? This is not less than 0.05, so we don't have enough evidence to reject H0. Since the p-value of 0.205, oops, is not less than the alpha level of 0.05, we do not have enough evidence. We do not have enough evidence to reject H0. And then the final question is, what does that mean in terms of this question, right? Is there sufficient evidence to support the claim that women in different age categories have different mean blood pressure levels? No. And we just rephrase the question as an answer. No, there is not sufficient evidence to support the claim that women in different age categories have different mean blood pressure levels. But I think I might have to steal it for just so I can write that out. And I'm just going to put it down here. Question 4. Therefore, there is not sufficient evidence to support the claim that women in different age categories, kind of boring, in different age categories have different mean blood pressure levels. Ta-da. So next week, chapter 11, it's an itty bitty chapter and it's our last one. Fun, right? So then just to give you an overview, right? So you're gonna read chapter 11 for next week. And then we'll talk about chapter 11, of course. And then we'll do a final exam review class, right? Only reviewing material, right? Final exam. And then we've got a chapter 12 bonus mark day. How about that? Next week, just so you know, we're just in the first probably 15 minutes or so. You guys have to do an evaluation on me. So that's what we'll do for the first little bit. So please come. If only for the first 15 minutes. No, you guys always come. All right. No questions, comments, concerns? See you next week.
What's chapter 12?
Well, it's because chapter 12 is important, but it's not typically on the final exam. So I just decided we'll just talk about it. You guys will have the opportunity for some bonus marks. Because the final exam's already done, right? So it's like, so what can I do to lure you guys back for one last day?
That's the only way to put other.
Yeah, I'm like, bonus marks.
Yeah, what are our second assignments?
I was just marking them. Yeah. So I'm working through them, and then I'll email them back. Yeah. Yeah.